Alright, so hello and welcome. Howdy. It's been a bit. This problem is an interesting question. I forgot that I had actually solved this problem already, so this is kind of going to be like a very quick recap, I suppose, or try to be somewhat quick. We'll see how it goes. So, oh, no, sorry, not we'll see how it goes. I already know how it's going to go. I already solved it. But yeah, I solved this problem already. Forgot that I was going to start solving problems beforehand and then didn't just show the answers. So this is actually, I've already solved this one, so I don't know what the answer is. But this is an interesting question. So, okay. So it says, the Hamming distance between two integers is the number of positions at which the corresponding bits are different. Excuse me. Given an integer array nums, return the sum of Hamming distances between all the pairs of the integers in nums. 4, 14, 2 gives you 6. Explanation. Binary representation 4 is 0, 1, 0, 0, and 14 is 1, 1, 1, 0, and 2 is 0, 0, 1, 0. Just showing the 4 bits relevant. In this case, answer is going to be the Hamming distance of 4 and 14, plus the Hamming distance of 4 and 2, plus the Hamming distance of 14 and 2, which is 2 plus 2 plus 2 is 6. And 4, 14, and 4 is 4. So what they're saying is, for every pair of numbers that you can have in your array, there's going to be a Hamming distance that you can calculate, right? So obviously there's n choose 2 pairs, which is quadratic number of pairs, and for each number, each pair, each of the bits that are different, so if you take the XOR of the numbers and you add all the bits that are still there, that sum, if you add all those, like count the number of bits that are the same, that is the Hamming distance, right? So obviously, it just gave you kind of like a quadratic time algorithm. Like you can loop through all the different pairs, and then you can do that probably just as a double for loop, and sort of one index from left to from 0 to the or left to right, 0 to the size of the array, and then another index that's sort of just one spot in front of it, starting from sort of the one spot ahead of the previous value, and you can just do a simple sort of round robin. That's what that's called, simple round robin quadratic time algorithm, and then obviously, like I said, you could just do an XOR and then count the bits that are there still left after the XOR. Or you could do a similar thing, which is like for each bit count whether or not add 1 if the bits are not equal, and add 0 if the bits are equal, right? So like I said, I actually know of the answer to this, and that I don't think is efficient enough, though. Probably won't be efficient enough if you do it that way. However, what's interesting is you can do a linear time algorithm where, as it turns out, because you're adding all of these different pairs together, or considering all these different pairs, each individual, if you just consider a single bit for every number, sort of one index, I guess there's a certain index for the bits, so one particular bit for all of the different numbers, they can only ever be 0 or 1. And what you'll notice is that if you were to group all the zeros and all of the ones, all the pairs that have a 0, pick any pair that has a 0, then every other 0, when you consider those pairs, will contribute 0 to the Hamming distance. But every other 1 will contribute a 1. So you have, for each 0 paired with each 1, you actually add 1. And that's for all the zeros. So for all the zeros, you'll have all the ones, you add a 1. What that means is that your Hamming distance for that particular bit is going to be exactly equal to the number of zeros times the number of ones, right? That's what addition is that for every 0, you add a 1 of all of the ones. So that's just a multiplication of those two things. So you can just count how many numbers have a 0 here, how many numbers have a 1 here, multiply those two and add that to the Hamming distance. You can do that for every bit. And that gives you the solution, believe it or not. It's actually that simple. And even you can go further. You don't need to count all the zeros and ones because you know how many numbers there are. You could just count the zeros, for instance, or just count the ones, for instance, and multiply that by the difference between the number of ones and the total number of numbers. And do that for every bit. And then you're done. That's linear time. I think there's a better way to do this, a faster way that uses less memory. There's even more clever way. I want to say doing something with XORs, but I haven't figured out that one yet. Haven't figured that out. It's probably somewhere in the discussion. But yes, that's the solution, and I'll code that in a moment. So here we go. We're a 5-6 minute video. Yeah, I don't know. Can you can you XOR these things somehow? I don't know. I'm sure there's another way to do this, but I don't know. Now, there's something also really subtle here, and that has to do with the bounds on nums of I, 10 raised to the 9th. I'm going to use a kind of a special for loop to do this, but because 10 to the 9th is exactly, so basically the number in an unsigned integer, the number of numbers that you can, an assigned integer, the number of positive integers you can fit in there is like something like 2,100,000,400,000, something like that. 2,140,000,000 and something below that. So if you divide by 2, it's still larger than a billion, which means that you can if you're only considering numbers between I think it's 0 or 1, 0 and 1 inclusive, 0 and 1 billion inclusive, then you don't need the last bit on your signed integer. So that's a very subtle thing, but that'll be useful in keeping our loop kind of simple here. So I'll show you the sort of what this looks like. It's pretty straightforward, actually, calculation once you kind of have the idea. So you can do auto, do const int x nums. We're going to do for. I actually want to do it the other way around. I want to do that on the outside, this on the inside, and the other one on the outside. So we're going to do, I think that was kind of clumsy, but that's okay. So int, we're going to call it bit equals 1, bit is less than a billion, 1, 2, 3, 4, 5, 6, 7, 8, actually, it could be less than or equal to, it really doesn't matter. 1, 2, 3, 4, 5, 6, 7, 8, 9. You can also do this too. This actually works also. I wonder if you can do, let's call it, could I do this? This actually should be, I think, the 31st. I don't know about this. Yeah, I don't use that too often. Const expression, final int, upper bound, 1 bit shifted to the left 31 times. So I think it's actually 30 times we want to do. That's a good question. Is it 30 times or 31 times? I think it's 31. Let's actually run this code to see what happens. I didn't do it this way last time, but we could probably do it this way. Hi! Currently I'm playing basketball. Talk to you later. Okay. Take care, Melito. It's good chatting with you. Enjoy. Hi. Hello. Welcome back. Hello, hello. Can we do final? Is there a way to, hold on. I don't use this too much, the final. When I click the search button, I tend to think that it's the create account button, and for some reason I think I'm logging in. Virtual function cannot be overwritten in a derived class, or that a class cannot be inherited from. Oh, okay. Java final is slightly different from final in C++. Overrides another overrider specifier. Oh, virtual functions are strictly. Oh, that's interesting. Okay, declared functions, or just I guess you call it virtual. Oh, I didn't know that. Okay, so if I'm using a final wrong, overrides another virtual function. Oh, that's interesting. Immediately after. By the way, I think the LeetCode substitution principle would make override not really a good idea. Well, I guess if the other function is virtual, then I guess it's fine. So never mind. I guess it's fine. Overrides another virtual function. So override but does not override. Non-static member function virtual and supports dynamic dispatch only appear in the declare specifier sequence. The initial declaration of a non-static member function is declared in the class definition. Virtual functions are member functions. Its behavior can be overridden in derived classes as opposed to non-virtual functions. The overriding behavior is preserved even if there is, no compile time information about the actual type of the class. That is to say, if a derived class is handled using pointer reference to the base class, call to an overridden virtual function would invoke the behavior defined in the derived class. Such a function call is known as virtual function call or virtual call. Virtual function call is suppressed if the function is selected using qualified name lookup, that is, if the function name appears to the right of the scope resolution operator. Interesting. Function, yeah, that's kind of interesting. Okay. So void virtual override is optional. Void f derived base derived. So base derived base b base dr d type is base as well. Prints base, prints derived f. I was just tinkering with something like this too before, just not too recently. Br dr. Okay, but this is virtual, means it's overridden. So BP and DP, virtual function call through pointer, non-virtual function call, space. So if you specify though, this will always print base on BR or DR. That's interesting. So this will use what they call virtual dispatch. But you can use a qualified name to not do for virtual dispatch. Also forgive me, smelling my hands while I'm messing with my face here. Interesting. So I have more examples though of things. Name lookup, virtual, final. Oh, they do have a final. Oh yeah. Final is functions declare the specifier and another function attempts to override it. The program is ill-formed. Attempts to override final BF. So, actually, wait. I'm a little confused because if a virtual function is intended to be overridden, then now a virtual function may or may not. So, a pure virtual function has no implementation. Set it equal to 0, creates an abstract, makes the class abstract. But a virtual function could be does have an implementation typically. If it's final, that means that nothing can override it. So that's kind of weird because why would you have a that's actually super weird. Why would you have final? Why would you? What's the use case for this? Or that a class cannot be inherited from. What are the use cases for this though? Why would you do this? So struct B is final, we can't inherit. Right? Can't extend it basically. And apply to member function. Class appears at the beginning of the class, definition immediately after the name of the class. Now what's interesting though about virtual functions is that you don't necessarily need to specify the virtual specifier to override a function. Yeah, so okay, so this is the difference. So as opposed to non-virtual functions, the overriding behavior is preserved even if there is no compile time information about the actual type of the class. Okay, that's super confusing, but basically you can override non-virtual functions too, but there's a difference, and this is the difference. As opposed to non-virtual functions, the overriding behavior is preserved even if there is no compile time information about the actual type of the class. So if there's no compile time information about the actual type of the class, so you don't know what the type of the class is at compile time, the virtual function will still have overriding behavior. So basically, if you look here, both of these references are to bases. Even though you call the base, the derived class, because we used virtual, will still call the derived function. That is so confusing, but it's really interesting. So if we go to our compiler and use a similar, and I realize this is so different this is going way off from what we were originally doing, but that's okay. I installed G++, so this is kind of a new addition here. Let's do virtual test. Let's do it this way. We'll say include IOStream int main, and let me know if this is too small to read to see. I think this is large enough. Can we? There we go. That's nice and big. I like that. Perfect. So, all right. So what we're going to say is we have class A, class B extends A, and we can put these. I mean, we could put these inside the main, but we're going to keep them out here. Right. We have these two classes, and we're going to have. Excuse me. We'll just say F, right? Void F, and yeah. And actually, what we're gonna do, we're gonna return a string. Whoops. Base string. And we're gonna say derived string. You know what, actually, I think it's better to do the other way around. Oops, whoa. Vim is pretty interesting, but I don't, sort of don't use it properly, I guess. Alright, so standard cout. And, whoops. And the same thing up here. Okay, so, okay, and we want to, you hear that noise every so often. If That hopefully you don't hear that. You'll probably hear it from time to time. I'll have to kind of figure out how to avoid that on Windows when using Vim. But here, if we do base, so we say A, B, B, and we'll say, so the base is A. Oh, we should probably call this base and derived. That's probably better. I kind of like the convention to name your classes with, instead of using camel case, to use snake case. I think generally the convention is to use capitalized base classes, so we'll do that. So we'll do base class and derived. And we'll do the same thing we did. They have here base and B and D, but here's what's interesting. So we're going to do virtual FV. Virtual base string. And we're going to say okay, so this is the interesting part. Or this is the difference. Virtual derived string. Derived string. Divide is probably not what I want. Okay. Alrighty. So, base reference is B, or just B, or yeah, we'll do pointer. Base pointer is B, and base pointer D pointer D, and then now we say. So here's the differences, right? BP, F, BP, F virtual, DP, F, and DP, F virtual, right? So what's interesting is how this is going to, when you compile this, what this ends up looking like. And my mistake, because I forgot that classes are public by are actually private by default. So the difference between a class and a struct is all element members are public by default, and public by default, whereas a class, all the members are private by default. What does that say? Also, whoa. Yeah, okay. What's the error? Virtual in member function, no return statement, and function returning non-void. Oh, why does it say int? Wait, why are these ints? I don't know why is that. I'm sorry. I missed that. And you know what we actually want to do? We want to override over here. Okay. Base pointer. Base is an inaccessible base of derived. You what? Really? Why is that? Oh, these are references. Oh, pointers. Oh yeah, the pointers and the references, the behavior should be pretty much the same. Wait, what? Why is this inaccessible? I have almost the same code, it's just we're using classes instead of structs. Is it because of the classes? Does it need to be declared public? What am I missing here? Something feels weird, feels wrong about this. Okay, that's why. Got it. Okay. Yeah, because using structs, everything's public by default, but actually, even the inheritance seems to be private by default with when you're inheriting. So if you inherit a class, it's actually with structs, it's going to be public inheritance by default, but it'll be looks like it's private inheritance by default through. Can you do protected? By that's kind of interesting. Oh yeah, even protected is not going to work either. That's kind of neat. It's got to be public. Oh, cool. That's a super subtle thing. I would not get that right in a quiz, I guess. In a quiz. Or I wouldn't have without testing it here. That's a good thing. It's good to just kind of mess around with code. But yeah, so public inheritance, private inheritance matters. Classes are privately inherited by default. Is it private or protected? I think it could be protected or private, not necessarily public though. It's not public though. Public member access, protected member access, private member access, inheritance. Yeah. We want the different inheritance. Class type, declare with class or struct, maybe declare as derived from one or more base classes, which in turn may be derived from their own base classes, forming an inheritance hierarchy, the list of base classes provided in the base clause of the class declaration syntax. The base clause consists of the character semicolon, or colon rather, followed by a comma separated list of one or more base specifiers. It's an optional sequence of any number of attributes, access specifier, private, public, or protected, keyword virtual, one of. So this is attribute, access specifier, virtual specifier, class declares. Oh, that's really interesting. So base specifiers. There's a virtual specifier too. You can do virtual inheritance, I guess. Virtual specifier and access specifier may appear in any order. Elaborated specifier cannot directly appear as class or declared type due to syntax limitations. Oh, elaborated type specifier. May be used to refer to previously declared class name, class structure union, or to previously declared enum name, even if the name was hidden by a non-type declaration. They may also be used to declare new class names. Whoa. Explanation, form 3 is a special case. So this is like really unusual to me. elaborated type specifier. That's like a pretty unusual thing for me. I would not use that too often, I think. Special case elaborated type specifier, usually referred to as a forward declaration of classes for the description of Form 3 forward declaration. Following only apply to Form 1 and 2, class name or enum name, and the elaborated type specifier may either be a simple identifier or be a qualified ID. Name is looked up using unqualified name lookup or qualified name lookup depending on their appearance. Non-type names are not considered. So I don't really understand what this means, elaborated type specifier. Declaration of the following form, class key attribute identifier declares a class type which will be defined later in the scope. Until the definition appears, this class name has incomplete type. This allows classes that refer to each other. Oh, okay, you forward declare a vector. The matrix can use a vector, it hasn't been defined yet, and then a vector can use a matrix, which has been defined above here. So you use a forward declaration. Okay, I'm familiar with that actually. But elaborated type specifier is class key, class name, enum name, class key one of class struct union. Class name, the name of previously declared type, class type, optionally qualified, or an identifier not previously declared as a type name. So it could be a previously declared class type or an identifier not previously declared as a type name. Interesting. And then an enum name previously declared or optionally qualified. Previously declared enumeration type, optionally qualified. One elaborated type specifier for a class type, elaborated type specifier for an enumeration type, a declaration that consists of solely of an elaborated type specifier always declares a class type named by identifier in the scope that contains the declaration. I'm so confused by this. What is the difference between this and a regular type specifier? Opaque enum declaration resembles 3, but the enum type is a complete type after an opaque enum declaration. Interesting. Okay. Kind of struggling to follow. Special case of elaborated type specifier usually referred to as a forward declaration of classes for the description of Form 3, see forward declaration. Following only apply to Form 1 and 2. Okay, so this is Form 1 and 2, but this is a forward declaration. Until the definition appears, the class has incomplete type. Okay. Classes refer to each other, and a particular source file uses pointers references to the class. This makes it possible to reduce and include dependencies. Forward declaration of standard row stream. Not really sure I'm following. I don't know, I'm kind of struggling. Appears in the local scope, it hides behind previously declared class variable function other declaration. I think it's too many things at once. I'm kind of like, hides previously declared class variable function all the other declarations of the same name. It may appear in closing scopes. So it appears in local scope. Note that a new class name may also be introduced by an elaborated type specifier which appears as part of another declaration, but only if name lookup can't find a previously declared class of the same name. Right. Okay. Not really following elaborated type specifier. I'll have to read that another time. I don't know. It's super unusual to me. But yeah, that came up. I don't know. This is like a bit unusual. Also, we're kind of using a bit of time. Yeah, 30 minutes or so. All right, we'll probably go solve the problem. We'll come back to this another time. But to kind of get back to what we were talking about, this is not where you use final. Bottom line. Final is for virtual functions, and we kind of went down a whole rabbit hole here where so what's interesting is, right, using the, if we look at our program, these pointers are pointing to references for B and reference for D, but they're both base pointers for the for the function that's not virtual and overridden, the F and F, right? We get base string and base string. So because it's not overridden, both times you're actually going to get the compile time type rather than the runtime type. It'll actually run the base function, right? Which is pretty interesting. However, you make the function virtual, then it'll do virtual dispatch, perform virtual dispatching, take the runtime, the runtime type. So BP will be the virtual base string because it's a virtual base, but DP, the pointer of the derived pointer, will actually give you the virtual derived string because it's using using a sort of virtual lookup, and because it was named virtual, it sort of overrides. So that's really interesting. I don't know if that's called virtual dispatch. I think it's called the virtual dispatch. Super interesting, but yeah, that's kind of neat. Yeah. So that the override specifier. Both cases, either override or final, or final override, override final. So you can make the override final also. The last time you override it, the last time it's going to be defined. A member function declaration or definition override specifier ensures that the function is virtual and is overriding a virtual function of the base class. Ill-formed if this is not true. Identifier special meaning when used after member function declarators. It's not a reserved keyword otherwise. Interesting. It's only reserved word in some cases. So dynamic dispatch, that's what's called. Yeah, virtual dispatch or dynamic dispatch may only appear. Specifies that a non-static member function is virtual and supports dynamic dispatch. It doesn't necessarily support dynamic dispatch though if you don't use a virtual specifier. Non-virtual override is preserved even if there is no compile time information about the actual type of the class. That is to say, if a derived class is handled using pointer reference to the base class, a call to an overridden virtual function would invoke the behavior defined in the derived class. Such a function call is known as virtual function call or virtual call. Virtual function call is suppressed if the function is selected using qualified name lookup. So you suppress it even if it's a virtual function. Virtual function dynamic dispatch can be suppressed by using a qualified name lookup. Yeah, okay, interesting. All right, let's close. We'll keep these open, but let me just get back to this question. So, yeah, so you can use this upper bound, use a constant expression, and then just say as long as bit is less than or equal to upper bound, then you'd say also wait, what? Shouldn't this? Oh, this I was gonna say this loop got optimized out. I was gonna say this loop should call t, or just c. Let's say count. We're gonna say if bit and x is greater than 0. You really could just do bit and x, but it doesn't. You don't actually need the greater than 0 plus count. And then we're going to say ret plus equals count times nums dot size minus the count, and then return ret. And that should give you what you're looking for. Oh, I guess not. Really? What? Wait a minute, what? What am I missing here? Did something wrong here. Did something wrong here. Yeah, this isn't getting called at all. Bit is 1, bits less than or equal to upper bound. Upper bound. Maybe it overflowed. I was kind of afraid that might be the case. If you bit shifted to the left 31 times, it might overflow. Ah, it did overflow. Okay. That's my mistake. That's my mistake. Runtime error. Left shift of negative value. Okay, interesting. Yeah, so actually this would be like this. Okay. Not as good, I think. So you can do less than. It's maybe easier. A little confusing, but yeah, so you could bit shift this one more time. Wait, actually, that was what I was going for. Oh no, you can't. If you bit shift it one more time, so okay, so that's interesting. So if you bit shift this one more time, this actually goes to the signed bit of the unsigned integer. Right, so it's, you can do 2 raised to the 31st minus 1 is the largest value you can get with an unsigned int. Right, so you do something like this, but it's actually going to be something. Okay. Actually, runtime error here, but yeah, this number. This is the largest number you can get with an int, and then if you take off this 1, it'll overflow, and you'll probably get some kind of error again. Yeah. Yeah, there you go. Okay, that's what we're running into. That's pretty interesting. So, really what I was going for was actually what is this? Is this a million? Or, yeah, a billion? Yeah, this is actually what I was going for, this number. But what's interesting about that is that if you say this is less than or equal to that, since I actually used a number that's a power of 2, if you say this is less than or equal to, then it'll actually trigger on that on this number, a billion, and then it'll multiply by 2 again, and that'll actually push you over to overflow, and then you get a runtime error. Excuse me, left shift of a negative value. Yeah, that's really super interesting. So I kind of wanted to make this simple by using 1 to the 30th, but actually it makes it not very simple, because what you'd want to do is less than or equal to for a billion, and then that ends up being the bit right before that sort of jump, but if you put it directly on it, then you have to do less than. So that's super interesting. I don't know. I guess this is fine, but yeah, there's like basically just like a simplification you can use because you're like right under a billion. But I don't know, I kind of wasted like a lot of not a waste of time. I spent a lot of time kind of talking about this, but yeah, this should work for all the cases that you can have now. We'll throw in like 1, 10, 100, 1,000, 10,000, 100, 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, we'll try those. See how we do. Yeah, I think this is correct. Let's give it a shot. little nervous to hit the button, but I think it's right. Yeah. So this is what I was describing before about like you just basically for each bit you can count the number of numbers that have zeros, the number of numbers that have ones, and then multiply those two together, and then add for each bit. Add those numbers, multiply those two numbers, add them together, and you get the number you need. Now, the thing to note here is that you notice we're not 100% on the memory or the runtime. We're very close on the runtime. We're quite good on the runtime. We're not perfect. So I would suggest there might be a better way to do this. I just don't know about. And that could be the case. I want to say this should be inlined or something, but or this should only be calculated once. Yeah, interesting. I don't know. I don't know how to make this faster. I don't think we need these parts also. I don't think it makes it any faster, but actually makes it slower. Interesting. Huh. I guess because it's in, I don't know why it would be slower. Anyway, alright, so that's that problem. Yeah, really interesting problem, but not too crazy. I don't know, there's probably a way to do this that's more efficient. It's probably, like, there's got to be a way that you can get 100%. That's fast, and also another way that uses less memory. There's got to be something that I'm missing. We'll leave it for now. We don't need to go too crazy, spending all this time trying to make this better. So yeah, that's this question. Like I said, I already solved it. Also, I have my volume is way up. I didn't realize that. Turn that down now. Sorry. Sounds like I'm yelling in the microphone. So yeah, thanks for watching. Talk to you soon, and have a good rest of your day. Actually, I'm gonna stream another problem shortly. So yeah, stay tuned.